Okay, good morning, everybody. Can you hear me okay?
Yes, sir.
Yep.
Good. All right, good. Good to hear from you all. Hope you're all doing okay. Hope you all had a good weekend. And yeah, so we are going to, as you know, we have the test later this week. So I'll post the test Wednesday morning. Wednesday, we won't meet for class, but I'll be in this room just for questions if you have any on the test. And you'll have until Monday to finish the test. So you have plenty of time to work around your work schedules and other classes. If there's any problems with that, just let me know. We can be pretty flexible. There's 3 students in this class, so we can be pretty flexible. So today I wanted to start our next section, which is kind of the foundations of quantum mechanics. But before we do so, I had realized last week that I had this worksheet that I never gave to you all. I think would be kind of a nice review of some of the topics from early in the relativity chapters. So I thought maybe we could just kind of go through this today. So I just sent it in the chat box. And let's take a few minutes to think through these problems. I would say the first 2 problems aren't too bad. And in fact, if you just want to think of them conceptually and kind of define what equation you would use and what you consider to be for example, the proper time or the proper length. You don't necessarily have to plug it all into your calculator. We can kind of go through those relatively quickly. The third one is a little bit trickier. It may be fun to think about. But let's take 10 minutes and everybody spend a little bit of time thinking about these problems. We'll go through them and then we'll start the next chapter, if that sounds okay with everybody. Okay, hi everybody. I think that was about 10 minutes. Did everybody get a chance to at least think about all three problems a little bit? Maybe not solve them all, but have some put some thought into them.
Yeah.
Yeah.
Okay, good. Yeah, that's the most important thing. Is that instead of me just showing you answers, that we have some time to put some critical thought in and think about them. So, okay, let's just go through these. The first question, we have the spacecraft flying past the Earth, and person on board measures the length to be 400 meters. And the question is, what do we see on Earth? And so with this problem, we can recognize that the proper distance is 400 meters, right? Because that's from within the spaceship where both ends of the spaceship are at rest relative to that person. So that's the proper length of that spaceship. And so from any other frame, you'll see length contraction, right? If that spaceship is passing you, it'll be moving with respect to you. And so we can solve for L with our length contraction formula and find that since I already solved for gamma, which was 7, so that means that the actual length that we observe is going to be 56.4 meters. So that's really shrunk. Yeah, so it's kind of fun. It was the spacecraft now looks to be 7 times smaller. And if you had like a hangar or something and the spacecraft was flying through it, it could fit in a hangar that was only 60 meters wide, right? Even though in its frame it's 400 meters. So that's one of those neat things about relativity. Okay, and problem 2, I'm doing a problem on a spaceship, and you're looking at me as I pass you, moving at half the speed of light, and you observe me take 15 minutes. How long did it take in my frame? Well, here we can recognize that the observed time must be 15 minutes, not the proper time. Right, in the proper time, both events take place at the same place. So that's 15 minutes. And so we can solve for our proper time, delta tau, we'll call it here. And using our time dilation formula and that gamma of 1.15, find that this takes about 13 minutes. So in my frame, it took about 13 minutes to solve the problem. But in any other frame, you'll see time dilation, right? The shortest time is always going to be in the proper frame. So that's a good way to check your answer when you get to these problems, to make sure you made the right choice in terms of choosing the proper time and the observed time, right? It should always be that the shortest time is in the proper frame. Okay, so those are those 2 problems. Any questions on those? Didn't think so. They weren't too bad. So okay, this last problem is kind of an interesting one. So TRAPPIST-1 is a red dwarf star, and this is true. They've discovered a lot of planets around this star recently, and so the question is, could we go and reach the star and study those planets? And we know it takes 40 years to light to travel from Earth to TRAPPIST-1, so that's 40 light years away. We haven't spoken too much about light years yet, but I imagine most of you have heard of that distance unit as a light year in the past. And the question is it possible for you to reach it in 30 years? If so, how fast do you have to travel? And so, well, the first thing we can recognize is what is the proper distance. The proper distance is, in some cases, it may be harder to conceptualize if it's not like a rocket or some object that has some size. But you can always imagine there's just a giant measuring stick between Earth and this star, and then there is an object that distance. So we can recognize the proper distance is going to be 40 light years. Right, because from your perspective on the Earth, you're not moving and the TRAPPIST-1 isn't moving. While if you're traveling towards TRAPPIST-1, both the Earth and TRAPPIST-1 are moving with respect to you. Right, so the proper distance is 40 light years. And so that's the TRAPPIST distance in Earth's frame. And so in any other frame, if you're traveling towards it, that distance is going to be smaller because of length contraction. So we can write down that formula. L is equal to L naught over gamma. And so that's 40 light years divided by gamma. So the distance is going to appear shorter to you if you're traveling towards it. So presumably, if you travel fast enough, that distance will be short enough that you can get there in 30 years. But let's try to prove that. So in your frame, as you're traveling towards that star, that red dwarf, how far you travel divided by time is just your speed. Normal mechanics is applying in your frame. So your speed is just going to be distance over time. And we want to solve for that velocity, given that we want to take 30 years to make the trip. And the distance we're traveling is this length contracted distance, 40 light years divided by gamma, right? So this is basically what we have to solve to figure out how fast we have to move. But we do have a velocity both in here and in here, so we're going to have to do a little bit of work to solve for that velocity. But yeah, this is a good chance to practice also with the concept of a light year, right? So 1 light year is how far light travels in a year. So you could also write it as time times speed, right? So that's 1 year times c, right? So that's a conversion we can use here. And so let's try to simplify this equation using that conversion. I'm also just going to move the gamma and the v to the same side of the equation just for now. Gamma v is equal to 40 light years divided by 30 years. And well, if I multiply the numerator and the denominator by c, I get a light year in the denominator, and my light years canceled, right? 1 year times c is a light year, right? This becomes 40 light years times c divided by 30 light years. My light years cancel, and so I get a nice number that'll be easy to work with for the rest of the problem. 40 over 30 times c is equal to gamma v. And now it's a good amount of algebra to write out gamma in terms of v and manipulate it until you can solve for velocity. I don't think I need to go through all the algebra here, but if you go through all that algebra, you find that velocity ends up being equal to the square root of this ratio, 40 over 30 c squared divided by 1 minus 40 over 30 squared. And plugging in some numbers, we end up with this being 0.8 c, or 4/5 the speed of light. So that's how fast we have to go to make this trip in only 30 years. To travel 40 light years in only 30 years, and we have to travel 80% the speed of light. So that's a kind of a nice problem, a little bit more challenging, I would say. And I think it's worth it to maybe just check this and talk about it a little bit. So given that we found that the velocity is 4/5 c, we can now find what is the gamma corresponding to that. It's equal to 1 minus 4/5 squared. And so that ends up being equal to 5/3. So our gamma is 5/3. So let's check, what do we see in our frame? In our frame, we see that the distance is a proper distance divided by gamma. And so that's 40 light years divided by 5/3. And that ends up being 24 light years. So in our frame, we're only traveling 24 light years. And so that's what enables us to do it in 30 years in our frame. So we only age 30 years in our frame. So in our frame, we age 30 years. What about an Earth frame? In Earth frame, distance is velocity times time. And so they see us we're traveling a distance, our time is distance divided by velocity. They see us traveling 40 light years and traveling 0.8 c. And so that corresponds to 50 light years per c, or 50 years times c divided by c, or 50 years. So in Earth frame, it takes us 50 years to do the trip. We're doing 80% speed of light and going 40 light years. So it's going to take us 50 years to do that trip. Or in our frame, it only takes 30 years. And to kind of further test that, we can confirm that kind of the observed time in Earth's frame is going to equal gamma times the time in our frame. And so let's check that. 5/3 times 30 years is equal to 50 years. So everything kind of checks out. That from different perspectives, there's going to be different amounts of time elapsing and different distances traveled. So we see length contraction in our frame. We only travel 30 years. We only age 30 years as we're traveling 24 light years. Earth sees us age 50 years and traveling 40 light years. So that's an interesting problem from different perspectives. So any questions on that? Okay, so I think that was kind of a nice final problem for this section. So this is chapter 5 in the book. Obviously, we went a little bit beyond the chapter as we discussed it, but I hope you all enjoyed special relativity. It's really fun to think about, and this problem in particular, I think, is a good demonstration of that. That a star that is really far away, 40 light years, we could actually get to in less than that time from our perspective. And so I know if you're a sci-fi reader, you probably have read books where there are people take advantage of that time dilation to reach faraway stars. So cool. That's special relativity. Let's now start thinking about our next chapter. So the next kind of split it into two parts. The first part is going to be light behaving like particles, and the second half is going to be more matter behaving like waves, which is also going to be very interesting. And this is kind of our experimental and theoretical foundation of quantum mechanics. And there's some pictures here. We have a blacksmith shop with some metal glowing red and yellow, some black body radiation. So we're going to try to understand that a little bit more. We have some kind of fluorescent plastics on the top right. Some kind of materials, when they're exposed to perhaps ultraviolet lights, will have electrons rise up to higher energy levels and then drop back down and emit visible light. And so these things will kind of glow. And in the bottom is photosensors. These are photomultiplier tubes within one of the biggest particle physics experiments in the world, the Super Kamiokande neutrino experiment. So this is a giant underground tank filled with water. And when neutrinos pass through this tank, some small fraction of them interact with the water and produce light called Cherenkov light. And that light is detected by thousands and thousands of these photosensors that rely on the photoelectric effect. So the photon comes in, knocks off an electron, and then they can detect that single electron. So these are very sensitive devices that are able to detect a single photon. So just a few representative pictures from everyday life that represent what we'll talk about in this chapter. So, okay. I'm going to go through a little bit of just a reminder of some things you've likely seen before in Physics 251, 261, or maybe some other classes. So just a quick reminder about waves. So since we're going to be talking about light, a wave is a traveling oscillation, right? Some kind of a propagating disturbance. And so you could have a transverse wave where you're moving the slinky up and down, and that displacement up and down is transferred down the slinky. Or you could have a longitudinal wave where you compress the slinky, and as it uncompresses, that propagates down the slinky also. So we have two types of waves, and we know waves can carry energy, right? A wave can knock you over, an earthquake can knock over a building, a sound wave can hurt your ears. So waves can carry energy. And just some of the language, of course, we use about waves, and we'll be using throughout the chapter. Wavelengths is a distance from one crest to one crest, or from one trough to one trough. Right, so it's typically, of course, drawn with the sine wave looking thing. And so the wavelength is a distance from crest to crest, or if you see ocean waves coming towards you, you can measure the physical distance in meters between those waves. Frequency, of course, is the number of times per second that the wave goes through a complete cycle. Number of crests passing a fixed point in space per second. So you can watch a little video of a wave moving past you and measure how many times per second a crest is passing you, and that is the frequency, right? And then amplitude is the height of the wave. And we may also know that amplitude is related to the energy of the wave. Right? A bigger, higher amplitude wave carries more energy. So that's just a little bit of a reminder of these concepts that we'll be using a lot in this chapter. And then, of course, EM waves, electromagnetic waves. So if you have an electric charge at rest, it has an electric field. If you move it, it produces a magnetic field. And so if you accelerate an electric charge up and down, as time varies, it'll produce electromagnetic wave, where you'll have a changing electric field and a changing magnetic field that propagate out from that accelerating particle. So we can have this kind of picture of electromagnetic wave. In this case, the wave is kind of propagating in the y direction, and we can kind of see the electric field is oscillating in the z direction, and the magnetic field is oscillating in the x direction. So that's kind of a picture we can have of electromagnetic wave, this kind of variation of those fields as a function of time and space. Oh yeah, these are fancy animations, forgot about that. So you can see the electric field and the magnetic field are always perpendicular to each other. And maybe this animation doesn't show it as much, but they'll typically have different amplitudes. So that's our kind of nice picture there. Other just kind of reminders about electromagnetic waves is they come at an infinite variety of frequencies and wavelengths, and we've given names to many of these different wavelengths. So the really, really long wavelengths are long radio waves. You know, these can be hundreds of miles long, right? And then somewhat shorter wavelengths of radio, we have the AM and the FM spectrum. So AM, we know, is a longer wavelength. They can propagate further on the Earth. They can kind of bounce off the atmosphere and go further than FM waves. But we know those are still pretty long wavelengths, you know, about the size of a meter or longer for those radio waves. We know the microwave spectrum is shorter wavelengths than radio. And then we have infrared, of course, which is now getting to, you know, pretty short wavelengths, 10 to the minus 4 to 10 to the minus 6 meters. And then, of course, we have the visible light spectrum. And we expand that out here into, we can kind of see that the wavelengths goes from, you know, 750 nanometers or so to 380 nanometers, with red being longer wavelengths and blue being shorter wavelengths and violet being even shorter wavelengths. And we've kind of arbitrarily, you know, it's a continuous spectrum, but we have these different colors we've defined, or RORG-BIV or RORG-BIV. I don't know what happened to indigo, we got rid of it. But we've got these different colors that have, you know, we do have scientific borderlines for the kind of boundaries of these colors, but there's a lot also to do here with kind of how your eye interprets these different colors when we think about what a color is. But there's a nice table here with kind of the typical interval for the different colors, red being 700 to 635 nanometers, which corresponds to a given frequency in the terahertz range of oscillations per second, so trillions of oscillations per second. Nanometer, I'm sure everybody has seen before, that's 10 to the minus 9 meter, so a billionth of a meter. But I also want to introduce the angstrom here. You've likely heard of an angstrom also, but if not, we'll try to define it. An angstrom is 10 to the minus 10 meters. So why do we define an extra name for this unit? Because it's about the size of an atom. And so for that reason, they've defined this special name for something that is 10 to the minus 10 meters. So a little bit smaller than a nanometer is an angstrom. So it's typically written with an A with a little circle on top. So chlorine atom is about 1 angstrom wide, where hydrogen is maybe half an angstrom wide. So because it has that relationship to atoms and in visualizing these units, it has a special name. And so you can relate an angstrom to a meter, 10 to the minus 10 meters. You can relate it to a nanometer. So there's 10 nanometers in an angstrom. I'm sorry, other way around. Or you can relate it to a micron. But either way, this is our visible spectrum. And then shorter wavelengths than that, we have ultraviolet. This is where we start to get to higher energies that we'll talk about later today. So you start to get into light that could injure you in some way, injure your eyes, or injure your skin, right? High energy ultraviolet rays can do that. And then X-rays, and then gamma rays, the really short wavelengths, we call gamma rays. So any questions on kind of our spectrum or these units? Okay. No questions, so okay. Here's a review of kind of plane waves related to electromagnetic waves. I've shown this slide before in this class and scared people. Don't worry, we're not going to be doing too much of this kind of tricky E&M type math in this class. This is just a little bit of review of things you've likely seen before in some way. That if we have a wave traveling in the z direction, this is our wave equation. It depends both on our location and the time. So it's a wave is an oscillation both in space and in time. The amplitude of electromagnetic field in our oscillating wave is E naught, or it's B naught for the magnetic amplitude. And we know that Faraday's law tells us a changing electric field will produce a magnetic field, changing magnetic field will produce electric field. Ampere's law again tells us a changing electric field will produce a magnetic field. So that's the main thing we have to have in our heads when we talk about waves in this class. And then we have just a couple of definitions. Angular frequency, you've seen before, omega is equal to 2 pi times the frequency. All right, so that's just a small change to get rid of 2 pi's when we write down these formula. We just don't want to write down 2 pi all the time. So we can define the angular frequency. We can also get rid of 2 pi's by defining the wave number k as being related to 1 over the wavelengths times 2 pi. So wave number is related to the wavelengths. And so again, the main reason to do that is to write these without 2 pi's. We know that waves can be polarized. And so we can take that as a direction of the electric field vector, right? That's the wave can be polarized and only go through certain polarized filters. And E cross B is always going to tell us the direction of travel. So we can use the right-hand rule to figure out the direction of travel. We also know that the wave speed is going to be the speed of light, c, and we have these nice relations that relate wavelength and frequency to the speed of light for our EM wave. Wavelength times frequency is just equal to the speed of light, so that makes conversions really easy. And we can also plug in these definitions of angular frequency and wave number to get this nice relation for a relationship between angular frequency, wave number, and the speed of light. And so these are just, these could be useful to you when solving some problems. So I wanted to make sure these are just written down for you in a place where you can reference them. Okay, so there's our wave propagating again. We know that the amplitude of electric field and the magnetic field is different. They relate by a factor of c. And we know that the amount of energy in a wave is given by this Poynting vector, given by E cross B divided by mu naught. So that's a measurement of how much energy per unit area is being carried by this wave. And so it's watts per meter squared. So it's energy per second per square meter. And again, not super critical to, we're not going to use this mathematically too much in this class. This is just kind of a conceptual overview of things you've likely seen before in some way. If you haven't, that's okay too. It's not going to be too pressing. And then we have a somewhat complicated equation here for the power But the main thing we want to know is that the power is how much energy per second is transmitted by the wave. We can also define intensity of a wave to be power per unit area. So that's energy per second per unit area is what we mean by intensity. And the main thing we have to know is that the energy per unit area per unit second transmitted by EM wave is related to the amplitude squared. Right, so that's something that is going to be typically true in all waves. That's the energy in a sound wave is related to the amplitude of the wave squared. So it's, a louder sound that's hurting your ears, it's carrying more energy in that wave. Okay. Some other things, of course, we know about waves is that they can exhibit superposition. So if I have two waves moving towards each other, they could precisely cancel out and then pass each other, right? So if a crest is meeting a trough, they'll add together and cancel each other. Or you can also have a crest meet a crest, and you get superposition where they're constructively interfering in a way that the amplitude is doubling, and then they pass each other, right? So we have this idea of superposition and the concept of interference. Again, the concept of destructive and constructive interference, where again, when a trough meets a crest, they cancel each other out, and so we get destructive interference. When a crest meets a crest, they add together to give you constructive interference. I like this picture a lot on the top right of two pebbles thrown into a pond or something like that. You can see these waves moving outwards from the location where the rock went into the water. And you can see where the waves are meeting gets even higher. Like right here is a little bit higher than right here. So that's constructive interference happening at those locations where crests are meeting crests. We also know that waves exhibit diffraction, right? Waves spread out when they pass through a small opening. So this is kind of a cool picture of waves coming in, pretty much plane waves. And so they've kind of drawn it in here. The waves are kind of coming in as a plane wave, and then they hit this rock, and then you can kind of see as it goes through this narrow opening, the waves are kind of curving outwards, and there's still going to be waves right behind these rocks because of diffraction. All right, so the waves can kind of pass through a small opening and expand outwards. So that's a little bit of a reminder of some just basic principles of waves. A little bit more about the diffraction, just a simulation of it. With a narrow opening, we can see a plane wave coming towards the narrow opening and then diffracting outwards from that opening. Sorry if these animations are a little delayed for all of you. See, with a more wide opening, we get a slightly different pattern. And in fact, we get some interference happening also, which we'll talk about later. But that's the main thing to know about waves exhibit diffraction. And waves exhibit interference. And so the most famous example of interference, something we'll talk about many times in this class, is the double slit experiment. Young's double slit experiment, where a plane wave is passed towards a wall with two slits cut into it. And so diffraction occurs in both of those slits. And so you get different locations on the wall where perhaps, the distance from the slit to this point versus the distance from this slit to this point maybe makes it so that two crests of that wave are both hitting this point at the same time, and you'll get constructive interference. Or maybe a crest is meeting a trough, but the pass length is different enough to be off by half a wavelength or something like that. And therefore you get destructive interference. And so we end up getting a beautiful diffraction pattern, right? We get bright spots and dark spots showing all this different interference from the light coming through these two slits. And so this is just a wonderful example of the wave-like nature of light. It's both diffracting and interfering to produce all of these bright and dark spots. We can do the geometry to figure out kind of the pass lights difference between X1 and X2 and figure out exactly where the bright spots and dark spots should be. And hopefully you've seen that before, maybe in a previous class, but it's, again, not super critical that we go through all the math right now. We want to understand it more just conceptually right now. And we'll go through some of this math later on in some examples, but for now, just know that you can predict the locations of the bright spots and the dark spots based on the path lengths differences between x1 and x2, right? If they differ by a unit of one wavelength, right? So that you're definitely going to get, this is going through maybe 2 cycles as it passes from here to here. It's going through 3 cycles, so that in both places you're getting a crest at the same time. You'll get constructive interference. Otherwise, if they're off by a half wavelength, you'll get a destructive interference. Okay, and we can actually predict the location on the wall, the actual distance in meters, using these formula, where those maxima and where those minima will occur. And maybe you've also seen diffraction gratings before. This is, instead of having 2 slits, putting hundreds of slits in a material. And so when you do this, again, you get diffraction as the light passes through the grating, but you get a different wavelengths. If your source light has many different wavelengths are going to bend different amounts as they pass through this grating, and you get the effect of a prism. So if you look at what a prism will do, right, like white light passing through a prism, the red will bend a different amount than the blue, and so you'll get this spread out colors. The same thing will happen with a diffraction grating. And so if you look at a light bulb through a diffraction grating, you see all these crazy rainbow of colors coming out from that white light. And you can also, shoot a laser through a diffraction grating, and you can kind of see that we're getting very distinctive bright spots and dark spots. So with a diffraction grating, you get these very distinctive locations where that light bends to, where you get constructive interference, and that tells you something about the wavelengths. And so diffraction gratings can be used for taking spectra or things like that. But anyway, this is, again, just something which we'll use for examples in the future, so we want to have some foundational knowledge about these things. And the final thing about diffraction I want to mention is called Bragg diffraction. I don't know if you all have heard about this before or not. You can let me know later if so. But Bragg diffraction is something we can do with now shorter wavelengths EM waves. So something like a X-ray. You can shoot at a crystal, and crystals have this regular atomic structure to them. And so that atomic structure can actually cause diffraction and interference. And so if I have X-rays coming into this crystal, the path length difference between those going to the first layer and those going through the second layer of that crystal can have a path length which is a multiple of a wavelength, and therefore you'd get constructive interference. Or they could differ, or maybe at a slightly different angle, the path lengths will differ in such a way that you have destructive interference. And so you can get these interference patterns from crystals. This is a very common way to study the atomic structure. Different atomic structures produce different diffraction patterns, or Bragg diffraction when we're talking about X-rays. So here's a typical type of experiment. We have an X-ray tube, something emitting X-rays, bouncing off a crystal and measuring the amount of X-rays at different angles. As you vary that angle, you'll get a variation of intensities due to constructive and deconstructive interference. And so this is a common way to study crystals. This is a part of how DNA was discovered, for example, the double helix structure of DNA. Rosalind Franklin famously did all these experiments to kind of show this double helix type structure in the DNA, with, of course, Watson and Crick got all the credit, but Rosalind Franklin did the work for doing those studies. So that's Bragg diffraction. So that leads us to, so that's kind of all of our review. And remember, this is modern physics, so we're talking about everything that's happened since 1900 or so, and just coming into the year 1900, thanks to Young's double slit experiment and all these other experiments, the wave-like nature of light was pretty well understood, right? They understood that a single slit will produce this kind of diffraction pattern where you have this wide, this bright wide pulse, which is much wider than the slit due to diffraction. And you also still get destructive and constructive interference at higher angles from light passing through different sides of the slit. So here's what a laser passing through a single slit would look like from a very narrow single slit. You get this wide peak in the middle, and then some destructive area where you don't have any light, and then a constructive peak, etc. Or if you pass it through a double slit, you get many, many more interference patterns. And so this is what the pattern would look like for a double slit experiment. So summary, going into our modern physics era, the wave-like nature of light was pretty well accepted. And again, borrowing some slides from our first day of class where I tried to get everybody excited about modern physics, this question of black body radiation was posed around this time. Why do hot coals glow red or yellow? Why does lava grow yellow or red or orange? Why does a blacksmith shop metal glow red or orange? And around this time, they are also able to do really dedicated studies where they can measure the amount of light produced by a black body, the intensity of that light, again, the kind of energy per second per unit area for a given, each given wavelengths of light. And they were able to make these very precise studies. And at the time, they showed that the kind of maximum intensity light emitted by one of these hot objects varies with temperature. So the hotter the object is, the shorter the wavelengths would get. So you'd go from having kind of infrared radiation to red to orange to yellow to white as something kind of got hotter and hotter and hotter. And so this is our concept of black body radiation. So these aren't perfect black body radiators, but it's interesting to think about what is a perfect black body radiator. A perfect black body radiator is often modeled as being a black box or a black sphere, as we show it here, where light can come in and get fully absorbed on the black surface, right? So any light coming in does not go out again. There's no reflection at all, right? The black absorbs all of that light, and then this object will radiate at whatever temperature it is based on this black body radiation spectrum we're about to talk about. So this is kind of our model of a black body radiator. And here's the type of analysis they are able to do around the year 1900. They're able to measure the intensity of light at a given wavelength from different temperatures of glowing objects. So if you look at like a 3000 Kelvin object, it's mostly glowing in the infrared. Its peak is right here somewhere in the infrared, but it is emitting a little bit in the visible spectrum, so it'll glow kind of red. Where something that is 4000 Kelvin will radiate at this very broad range of wavelengths, but the peak has moved to a shorter wavelength, right? And it's still mostly peaks in the infrared over here, but perhaps there's a little bit more visible light produced by that. And then as we get to 5000 Kelvin, the peak is now in the red. And now if we get to 6000 Kelvin, the peak is now over here or in the green. So we can kind of see that the peak of this distribution is going to shorter and shorter wavelengths as the temperature of our black body radiator increases. We can also see that the distribution is really broad. So although the peak may be in the green here, there is all colors of light being emitted by the black body radiator, and ultraviolet light and infrared light, right? So there's a huge spectrum, of course. And we can also see that the height of this peak and also the area under each of these peaks is increasing as the temperature increases, right? For 3000 Kelvin, the area under the curve is just this, where for 6000, all of this is kind of the area under the curve. So that tells us something about the amount of energy being emitted, that there's more energy emitted due to this thermal radiation for a hotter object, which shouldn't be too surprising. So this was the type of study they were able to do around that time. And so there are these two famous kind of empirical laws that were written down around that period of time. These were not theoretical laws. These are not things that, they were able to predict based on some fundamental knowledge of how the atoms were moving or anything like this. This was just looking at the data and plotting it and fitting a curve, basically, right? So there's a Wien's displacement law, which relates this peak, that location of the maximum wavelengths, to temperature. Basically, as the temperature increases, the wavelength decreases. So that's what they were measured, and it happens in this 1 over temperature type of a distribution, right? So if you just fit this blue line, you get something like this, and the constant of that fit will be this thing I call the B here. This doesn't really have a name, this constant. Often you see this equation just written out with a number, but here it is for you to use in solving problems. And the main thing here is this is an empirical law, right? It's observing the data and trying to fit it. And it's showing us that the max intensity wavelengths decreases with increasing temperature, right? Or the frequency increases with increasing temperature, because we know those are inverses of each other. So that's the first thing. And maybe you've seen that in high school physics before, perhaps. And then on the right, we have the Stefan-Boltzmann law, which tells us the amount of power radiated by a black body, and tells us that the function of the temperature to the 4th power. So power, or energy per unit time, and this is a function of temperature. So the amount of energy per unit time for a given temperature of black body is related to this constant, the Stefan-Boltzmann constant, which at the time they only just knew this number. They were able to just measure this number. But now we have a theoretical understanding of it, and it's actually equal to this interesting combination of other constants. So this knowledge came later, right? At first, they were just able to measure this constant. So we multiply that constant by the area of the black body emitter, the surface area, and multiply that by the temperature to the 4th power. So you can see as the temperature increases, the power emitted, the energy per unit time emitted, increases very rapidly, right? Temperature to the 4th power. And we can think about black bodies we know about. We know that the photosphere of a star is a pretty good approximation to a black body radiator. So our sun has a photosphere of 5,772 Kelvin. And so that makes its spectrum pretty close to the 6,000 Kelvin line or so, which means that the peak wavelengths emitted by the sun is somewhere in the kind of yellow-green range, which also happens to be the wavelengths of light that our eyes are most sensitive to, which is pretty interesting. And you can see that the vast majority of the energy emitted by that black body of our sun is in our visible range. Again, you can thank evolution for that. But we can also know that there's a lot of wavelengths of light emitted by the sun that we can't see. There's infrared and ultraviolet light that we can't see coming from the sun. And so, yeah, the sun's pretty neat. And let's talk about the sun just a little bit more. As I mentioned, stars are approximate black body radiators. And for example, if you look at our sun from space, it actually looks white, right? Because it's emitting, it's emitting most kind of in the yellow-green range, but it's emitting kind of at a very broad range of spectrum. And so to our eyes, when we see this broad range of the spectrum, we interpret that as being white light. And so the sun does look kind of white from space. And it's kind of the sunlight coming through our atmosphere where the blue light is scattered away that makes it look kind of yellow to us. And you can kind of prove this to yourself by looking at the path of the sun over some period of time. You can see when it's high in the sky, it looks pretty white. When it's low in the sky, it looks kind of more yellow orange, right? Because more of that blue light is being scattered away. But we can study the sun in a very wide range of colors and wavelengths. There's lots of space telescopes and Earth-based telescopes, which are continuously studying the sun. And so these are pretty cool experiments that are ongoing. And of course, we can see that the sun is emitting in a wide range of colors. And we can also look at, this is the actual spectrum of the sun in yellow. kind of what's hitting the top of the atmosphere is a yellow. And again, it looks pretty similar to our black body radiation prediction. And you can see it's peaking kind of in the yellow-green part of the spectrum. But we can also see in red what we can observe on Earth is that a lot of wavelengths are absorbed, depending on different, and we'll talk about absorption spectrum and once we understand more about quantum mechanics. But we can see a lot of the ultraviolet gets blocked out by the atmosphere. We can see a lot of the kind of blue and violet gets kind of scattered. We can see different infrared regions where almost no light is reaching us from the sun, right? Because our atmosphere is kind of absorbing those wavelengths of light, of course, leading to greenhouse effects and fun things like that too. Okay, that's just one example of a black body radiator. Of course, you're a black body radiator too. If you have a few $100s, you can buy a infrared camera and use it to study the world around you. You can see that infrared camera has no trouble seeing through a black plastic bag, right? Because you're still radiating in infrared. And you can see a cold-blooded caterpillar pretty clearly, and you can pretty clearly see which of these cups is containing hot liquid with an infrared camera. So you're radiating infrared mostly because your temperature is low, but it's still fun to observe the world in that way. So, okay. And you know that the glasses don't really transmit very much infrared. They're mostly not letting the infrareds through. Okay, so that's black body radiation. And as I mentioned on the first day of class, this was kind of a fundamental puzzle around the year 1900, because the kind of classical prediction of what this black body spectrum would look like was like what this orange line is doing. Was basically, it was predicting an infinite amount of energy at small wavelengths emitted by black body radiators. So that can't be right. And this is called the ultraviolet catastrophe, that everything should be kind of infinitely bright and blue and violet and ultraviolet light. So we're going to talk about this a little bit. The kind of foundational math that can predict what's called this Rayleigh-Jeans prediction is kind of beyond the scope of this class, but I'll kind of walk you through it just a little bit. And it's wrong, so it's not that critical that we understand it, but it's a kind of classical physics, thermodynamics type knowledge around the year 1900. And then Max Planck, of course, came along to make the prediction that actually fixed this puzzle. So the classical model of this is to have the model of black body radiator as, again, being just a cube where light can come in but not really come out. Everything gets absorbed within that cube. And because of the rules of E&M, we have to have the given voltage is a given voltage at each surface. So we need to have certain conditions that must be satisfied for these waves to be within this box. So therefore, we have to have waves that look like this, or like this, or like this, but we can't have any waves that have a large amplitude at the edge of the box. That just doesn't fit the boundary conditions. So basically, you have to add up all of these different types of waves that could be within that box, and then multiply them by the energy per wave. And that's how they made this classical kind of wrong prediction in calculating that energy per wave. They were using kind of classical thermodynamics, the Maxwell-Boltzmann distribution, where the number of things kind of oscillating in this object depends on temperature, and the mass here doesn't matter. We're just trying to get to a final prediction. Like this one, this was a Rayleigh-Jeans prediction that the intensity of light from a black body should depend on wavelengths. It should depend on temperature linearly and depend on wavelengths as 1 over the 4th power. And so this produces the wrong prediction that we saw earlier. The Rayleigh-Jeans prediction looks nothing like the actual data. Again, just know this kind of thermodynamics calculation to make that wrong prediction. So, okay. what Max Planck came and did was just said, okay, what if the energy of those vibrating atoms can't take any value, and in fact can only be just discrete pieces of energy where h is some constant, Planck's constant, and f is a frequency. And by making the energy discrete, basically you're changing the energy per mode, per standing wave, and you get a much different energy per mode. And putting this all together, you get a very different looking equation for intensity. And in fact, this equation predicts the black-body radiation spectrum really nicely. Right? So by making higher energy, higher frequencies, shorter wavelengths modes, higher energy, kind of made this curve turn down and made it so that you can't have an infinite amount of energy coming out of these radiators. And so that's the end. This is kind of the foundation of quantum mechanics, that we're going to find that energy is starting to be quantized. It's coming in these discrete packets. And Planck's prediction really nicely fitted the data that was taken around that time for the black body radiation spectrum. So that's the main thing we need to know, that Planck had this hypothesis that the amount of energy emitted by an oscillator is some discrete amount, where h is some frequency, h is some constant, f is a frequency. And this is the Planck's constant. This we're going to be using a lot in this class. It's usually lowercase h. It's 6.62 times 10 to the minus 34 joule seconds. You can also write it in terms of electron volts if that's helpful to you. And this is the radiation law. Basically, this is our formula that can predict the spectrum of this of a black body. So if you plug in a given temperature and a given wavelength, it'll tell you, that dot, for example. And so you can vary the wavelengths for a given temperature and get this black line. And the KB in here is Boltzmann's constant, so that's written down there for you too. So again, this class is very conceptual. We're trying to get exposed to a very wide variety of areas of modern physics, and so this is kind of the most important kind of conceptual thing that we're learning about here, is that discrete energy kind of solved the black body radiation puzzle. And so, as I said, Max Planck kind of stumbled on this. He was just playing around with the mass, and he kind of found that it worked. And so this led to a fundamental rethinking of the world around us. And just as kind of a nice example of this, we can talk about the cosmic microwave background, something we'll talk about a lot more when we get to the cosmology chapter. But the predictions of cosmology predict that the early universe was a hot, dense soup of plasma. So there was no atoms, there were no stars, there were no planets, no galaxies. It was just this hot, dense soup of electrons, protons, photons flying around, interacting with each other. As the universe expanded and cooled, those electrons and protons formed hydrogen. And then at that point, the photons weren't constantly being emitted and absorbed. At that point, photons could be emitted and just propagate through space and not be absorbed. And so it turns out those photons are still floating around in the universe. Those photons produced from that initial moment when atoms first formed, some of those photons are still floating around. At the time, they were these really hot, high energy photons, but now they're microwaves, because as the universe has expanded, the energy has actually been lost, and those wavelengths are now at longer wavelengths, microwaves. And you've probably heard of the microwave background before. It was discovered in 1965 by Penzias and Wilson. These two folks were not, another team was explicitly looking for the cosmic microwave background based on a prediction. They weren't looking for it. They just were trying to get this radio detector to work, and they were having all this noise in their detector. They thought it was birds or something like that. And in the end, it turned out they had actually discovered photons, which are still floating around from the Big Bang. So that's pretty neat. And then in the 90s, we had a satellite, the COBE satellite, which made pretty detailed measurements of the cosmic microwave background. And then in the 2000s, WMAP made much more precise measurements. And now we have Planck, which is currently operating space telescope, a lot of cosmologists, a lot of grad students studying cosmology are currently working on. And you can see that compared to COBE to WMAP to Planck, we see much higher detail of the kind of variations in this cosmic microwave background. On the left, we can see the kind of plane of the galaxy, and on the right, they've subtracted that out. And you can see there's these tiny variations these colors are kind of denoting very small variations in the wavelengths of light coming from the cosmic microwave background, like tiny, tiny, tiny variations. So it turns out that the wavelengths corresponding to this microwave that these experiments are measuring is about 1 millimeter. So these satellites in space are measuring this wavelengths of EM radiation coming from the Big Bang that's about 1 millimeter. And so assuming that that was a kind of a black body type emission, we can actually figure out the temperature of that black body. And so let's assume that that cosmic microwave background was a perfect black body radiator. And given this spectrum, this black body spectrum that these satellites can observe, what temperature do we expect that to be? Given that we know that max wavelengths, we can plug it into our Wien's displacement law, right? We know the wavelengths, we can solve for the temperature and find that that temperature is about 2.7 Kelvin. So 2.7 Kelvin is the temperature of the cosmic microwave background in the present day. So that's kind of present in all of space. So you can measure those photons anywhere in space, that 2.7 Kelvin photons. This is, again, a lot cooler than the original photons because over time the universe has expanded and the wavelength of the photon has grown. But that's a kind of a neat example for playing with these empirical laws and how they can help you think about solving some problems. So, okay, that's the CMB. Let's see, do we have time for, I think do we go to 1:45? I think we do, right? So we have 7 minutes, yeah. So I think we have time to start talking about the photoelectric effect. And again, this I showed you a little bit of on the first day of class, but this is the classic electroscope where you have a metal plate, and attached to that metal plate in this jar, presumably in a vacuum where there's no like atoms messing around with our experiment, we have this gold leaf. And so if I was to have a plastic rod or something that I've kind of rubbed a cloth on or something like that to give it a net charge, a net electric charge, touch that to this metal, and now I have a net negative charge on these metal plates, right? There are electrons now spread out all over this metal. And so since there's electrons on that bar and electrons on that gold foil, those are now repelling each other, right? And now if I have this repelling electron object on the metal plate, I can shine a light on that and see that they stop repelling each other. So somehow we must be knocking electrons off of that metal plate, and that's the photoelectric effect. And so this is a really nice demo of it with a real electroscope. So right now the electrons are repelling each other, and shine an ultraviolet light on it, and you can see that the electrons must have been knocked off. So that's our photoelectric effect. Here's our kind of picture of what's happening. Light is coming in and knocking off electrons. And so we're going to try to understand this a little bit more about how much energy do you need to actually knock off one of those electrons. And those electrons which fly off, we call photoelectrons. And the kind of current, how many electrons per second or how much charge per second is being knocked off of a surface, we call the photocurrent. And again, our classic physics model gets this wrong. It says that the amplitude of our wave is related to the intensity of the wave, and therefore related to the energy of the wave. So a brighter, higher amplitude wave should knock off more electrons. It should come off with more energy, and it shouldn't matter what color of light you're using because it's related not to the wavelength, but to the amplitude. But that's wrong, right? That's our classical prediction. And so that's, again, something we have to realize here. So here's our setup. I know this is a super busy slide, but I think this is kind of a nice image. So here's our basic setup. We have a vacuum tube. On that within that vacuum tube, we have this kind of curved metal plate. So that's the metal plate that we're going to shine a light onto. We also have a metal bar somewhere else in our vacuum tube. And so we can set up our experiment in different ways. We could set it up so that that metal bar has a positive charge on it, and the curved plate has a negative charge on it. And so when you shine light in and it knocks off one of these photoelectrons, well, they're negatively charged electrons in this vacuum, and there's a positive charge bar right here. So they'll be attracted towards that bar. They'll speed up towards that bar, right? Because they're increasing in energy due to that electric field. And they'll strike that bar, and they'll be registered as a current. And so you'll measure this photocurrent from that light hitting the cathode and knocking off these electrons. But what we can also do is we can reverse the voltage across this detector. So we can make the metal bar negatively charged and the metal plate positively charged. So now when you knock off an electron, some of them won't have enough energy to get to this wire, to this thin wire. They will be repelled by the negative charge here, and they'll go back and hit the metal plate. While some others may have high enough energy, they may come off with enough kinetic energy that even though they're losing energy as they move in this electric field towards this negative charge, which is repelling them, they still may be able to make it, right? They still may have enough energy to travel that distance with that force pushing against them. But if I increase the voltage and increase the voltage, at some point, no electrons coming off of that metal plate will make it to the wire here. Right? And so that enables us to measure what's called the stopping potential. How much potential difference do you have to make across these plates to make it so that no electrons make it to that wire? If you know that stopping potential, you can measure the kinetic energy of the maximum kinetic energy of those electrons coming off of that plate, right? Because again, they don't have quite enough kinetic energy to make it to that wire. And we know how much energy is between these two. We know the potential difference between these two metal objects. So here's an example of the experimental result. If I have some constant intensity light shining on the metal plate, and I have this metal plate negatively charged, I get pretty much a constant current. But as I, even if I totally turn off the voltage, I still get some current because those electrons are flying off in all directions, and some of them are hitting the metal wire. But as I start having this negative voltage and start making this metal wire negatively charged, fewer electrons that pop off are going to make it. So the current starts going down and down and down. So that's what we see in this graph until we get to the point where none of them, the current goes to zero. That's what we call our stopping potential, right? And we know that the work done by the electric force as we travel from here to here is given by charge times voltage. And so that must equal the change in the kinetic energy of those electrons. And they're losing kinetic energy as they travel towards a metal wire because this electric force is pushing against them. And so this enables us to measure kind of the maximum energy of the electrons being emitted, right? So these very few electrons that are making it when we're just below that stopping potential is pretty close to the highest energy electrons that are emitted from that metal plate. And so the maximum kinetic energy emitted is going to be related to the stopping potential of our experiment. So that's kind of our classic photoelectric experiment. I guess we're pretty much out of time, but we'll just leave it here that our experimental setup allows us to measure if photoelectrons are produced or not. So we could do this experiment with green light, with blue light, with red light, and see if photoelectrons are emitted or not. And if they are emitted, we can measure their energy. And so that's going to help us to do this experiment and make some interesting observations next time. So we won't talk about this until next Monday, because on Wednesday I'll have my kind of office hours, and you'll be mostly focused on relativity in the second half of this week. But I hope you're getting excited also about the next chapter. There's a lot of really cool observations about the world that we're going to get exposed to. So, okay, are there any questions to finish off here, or? Hope I'm not frozen.
No, you're good.
Okay, cool. So yeah, hope you're getting excited. Let me know if you have any questions. I'm going to get all the posted homeworks graded in the next day, and I'll have comments on Brightspace for you, so that'll help you in preparing and knowing if you've made any mistakes in the homeworks. I can help you on the test. And just let me know if you need any help, any questions, anything. Happy to help. So otherwise, have a good rest of your week, and look out for an announcement on Wednesday morning about the exam posted. And yeah, I'll be here in the Zoom room Wednesday during the normal class time if you have any questions. Sound good, everybody?
Yep, thank you.
Yeah, sounds good. Thanks.
Thank you.
Cool. Thanks, everybody. Have a great day.